All right, so we're going to continue with number 2 from page 890 that we were working at the end of the last video. So we had our function, our constraint. We set up this equation for Lagrange multipliers, which gives us this system of equations. And then we have our constraint down here. So in solving this, really what we're looking for are x and y. So I always tend to start with the easiest or the simplest of the 3 equations. So I'm going to start with number 2 and try to, it's probably beneficial you try to organize your algebra so you can go back and find the points that you need along the way, and you make sure you use all your information that you have here. So let's just put over here that I'm going to start with 2. So now, whenever I use equations, usually I'm trying to isolate a variable, which involves me dividing by some other variable. So before you divide by a value, you have to do one of 2 things: either ensure it's not 0, or consider the case when it is 0, and then also consider the case when it's not 0. So here my intuition would tell me, or my instinctively would say, okay, well, I'm going to solve this for lambda and plug whatever I get for lambda in up there. But to solve this for lambda, I need to divide both sides by 2y. So I would have to know that y is not 0. And there's nothing here so far that tells me that y cannot be 0. So what you do in that scenario is you just consider that case then. Now, if you have something in your 3 equations that tells you that the value can't be 0, then you can just use that, and then you can go ahead and divide by whatever that variable is. So if y is 0, and I'm still just looking at this equation, if y is 0, then that gives me that x would have to be 0 because my right side would be 0, so my left hand side is 0. So then x equals 0. And then you see what this pair does in your other equations. So if I put x equals 0 in here, I'm just going to get 1, and then y equals 0, I'll get 0. So 1 plus 0 equals 1. So this satisfies 3. So it's perfectly okay. Now, if something violates 3, you have to throw it out. You can't. It's something you cannot do because 3 is your constraint, or if it violates any of the other equations for that matter as well. Now, if I take y equals 0 and x equals 0, and I put in this first equation up here, I get 0 on the left. And on the right, I would just get lambda times 2. So I get 2 lambda equals 0, which would just tell me that lambda equals 0. And remember, early on I told you we really don't particularly care what lambda is as long as we can get what x and y are. So this tells me that I have a point. I have one of my points already is 0, 0. So let's put that over here. And I'll put it in a little circle or box or something. So I remember to go back to that point when it's time for me to plug my points in. All right, so now we've considered the case y is equal to 0. So now we know we're exhausting everything if we look at y is not equal to 0, because those are the only options for y. So if y is not equal to 0, then we're still working with equation 2 here. So now that y is not equal to 0, I can divide both sides of this by 2y. And I get lambda equals x over 2y. This lambda equals x over 2y, of course, doesn't help me with 3 because help me in 3 because there are no lambdas in there. So I will go back and use this in equation 1. So equation 1 now becomes y equals 2x plus 2 times x over 2y. All right, so now when we manipulate this, we multiply both sides by 2y and distribute the x on the right side. And then also at that point, everything will have a 2 in it as well, so we can divide everything through by 2. We would get 2y squared equals 2x squared plus 2x. And then dividing by 2, that just gives us y squared equals, let's say, x squared plus x. All right, so now we look and see, okay, what can we do with this? So we've used 2 and 1 to get to this point. So the only other place that we have is 3, is we're going to use this in 3. All right, so I'm going to go to the next page here. substituting that into 3, we get, so yeah, since you all are probably still on the same page, just put this 3 right below where we were just writing. So we don't want to go off to the left again and think we're starting over. I kind of like start my process on the left, and then I move over to the right and just stay there until I'm going to the next step. So if I had to go back and start all over and use another equation again, then I would start over at the left. But just to maintain order, once I get to the right, I just stay on the right hand side. All right, so we're putting in, so our equation was x plus 1 quantity squared plus y squared, and we just found out y squared is x squared plus x equals 1. All right, so if we simplify this, we get x squared plus 2x plus 1 plus x squared plus x equals 1, which gives us 2x squared plus 3x equals 0. 2x squared plus 3x equals 0. We can factor out an x from both of those. X times 2x plus 3 equals 0. And this tells us x equals 0, or 2x plus 3 equals 0, which says x equals negative 3 halves. All right, and remember we're looking for points x comma y, so we take both of these and substitute them back into our constraint equation. I mean, we could try to use one of the other equations, but it's not necessary. You can use your constraint equations, have x and y in there, but you can use whichever equations you want to substitute things back in there. All right, so here, when I put x equals 0 back in, or you can use the equation we got from 1 as well. It doesn't matter what you use. When I take this x equals 0 and I put it back into our constraint equation that we initially had, we already know that's going to give us y equals 0. So we already have that point, x equals 0, y equals 0. And then if I take x equals negative 3 halves and I plug it back into, I'm going to plug it back into this equation. That right there. And so if I put that in there, then I'm going to get y squared equals 9 over 4 minus 3 over 2. Or y squared equals 9 over 4 minus 6 over 4. So I get 3 over 4. So that tells me y equals plus or minus the square root of 3 over 2. So now we have our points 0, 0, negative 3 over 2, comma, root 3 over 2, and then negative 3 over 2, comma, negative root 3 over 2. All right, so that was in our two-step process. That was part A of the process. Now what we're going to do is take these points and we're going to substitute them back in. So we need to do f of 0, 0. And our f was x times y, so that's just going to be 0. F of negative 3 over 2, comma, root 3 over 2. So that's just going to be equal to negative 3 root 3 over 4. And then lastly, f of negative 3 over 2, comma, negative root 3 over 2. And that's going to give us positive 3 root 3 over 4. So we know that we have our min subject to this constraint is here, and our max subject to the constraint is there. All right, so next we're going to look at number 15. And we are still on page 890. Number 15 says, in the remaining exercises in this section, assume that the required extreme values exist. Find the points on the surface x squared minus y is equals 1 that are closest to the origin. So remember, we're looking for an objective and a constraint here. So they say closest. That means that we're looking at a distance. So in our constraint, they give us, so the key things we see in the problem are x squared minus yz equals 1, and we see the word closest. So closest means we're talking about a distance. So our objective is going to be the distance between whatever points that we're seeking. So find the points on the surface. So any point on that surface is going to have x, y, z coordinate that are closest to the origin. So we want the distance between these points x, y, the point x, y, and z in the origin to be as small as possible, which means our objective function is d equals the square root of x minus 0 quantity squared plus y minus 0 quantity squared plus z minus 0 quantity squared, which is the distance between x, y, and z in the origin. And then our constraint is that these points x, y, and z have to be on this surface. So constraint is that x squared minus yz has to be equal to 1. All right, so one thing to make note of is that when you have to do an optimization problem or a max-min problem and you're using a distance function, you're going to have to take derivatives. It's easier to just use this thing squared, and whatever points minimize the distance, those same points are going to minimize the square distance. So instead of using this, it's just going to make our life much easier with our derivatives without having this square root swimming around the whole time. So we're going to change our objective to f of x, y, z equals d squared, which is just equal to x squared plus y squared plus z squared. One thing to keep in mind for a problem like this one, so we have this function of 3 variables here. In 13.8, what we would do for a problem like this, because we didn't know Lagrange multipliers yet, is we would solve this for one of its variables, substitute that in here, and then approach the problem that way. So notice we can do some of the problems that we were able to do in 13.8 using this 13.9 approach, and vice versa. All right, so now we have our function f, and our function g is the left-hand side of this. So g of x, y, z equals x squared minus yz. All right, and now we need to set up the gradient of f equals lambda times the gradient of g. Now, instead of what I tend to do, I think on the first problem I probably wrote out each component of the gradient, each of f, each component of the gradient of g, and put them in this equation like this. Now I'm just going to take f sub x and I'm going to set it equal to lambda times g sub x. Make that my first equation. F sub y, set it equal to lambda times g sub y. F sub z, set it equal to lambda times g sub z, and then my constraint. So we're going to have 4 equations there. So I need my functions. So f sub x is 2x equals lambda times g sub y, g sub x, which is also 2x. And then f sub y is 2y equals lambda times g sub y, which is negative z. Then f sub z is 2z equals lambda times g sub z, which is negative y. And lastly, our constraint is x squared minus yz equals 1. So I'm going to label my equations to keep things organized. All right, so we have these 4 equations. Now, you start wherever you want to. You do your algebra however you want to, as long as you do it correctly. The level of complexity in all 3 of these first equations is the same. So I'm just going to start with number 1 and go in order from there. So, well, actually, no, 1 is easiest because that one has only x and lambda in it, whereas this has y, lambda, and z. This has y, lambda, and z. So this actually is the simplest one, number 1. All right, so starting with 1, we move everything over to the left-hand side, and it's 2x minus lambda times 2x equals 0. And we can factor out a 2x from this, and we get 1 minus 2x times 1 minus lambda equals 0. And now this tells us that x equals 0 or lambda equals 1. And we squeeze all the information we can out of 1, and now we're going to use that in one of these other equations. So I'm going to start with x equals 0, and then I'll get whatever I can out of that, and then I'll move over to lambda equals 1 and get whatever I can out of that. So for x equals 0, I'll put that on the margin and double underline that so I know that everything I'm writing right now, my x is 0 this entire time. So first, I'm going to use it. There are no x's in 2 or 3, so I have no choice but to use it in 4. So using that in 4 gives us that negative yz equals 1. If this product equals 1, that means neither one of those can be 0. So I can divide by either y or z to isolate one of them. I'll solve for y. So y equals negative 1 over z. All right, now I want to take this and use it somewhere. I could use it in 2 or 3. Doesn't matter. I'm going to use it in 2. So when I put that in 2, I get 2 times the negative 1 over z, equals lambda times negative z. So the negatives are going to cancel one another out, and I'll just get 2 over z equals lambda times z. And I solve this for lambda so I can use it in that third equation. And you could try to solve for z. The other issue is when you solve for z, you're going to get z squared. When you isolate z here, you're going to get z squared equals something. And I would prefer to avoid that because then you have a plus or minus that you have to deal with, which you may encounter it later, but I'll just go for lambda because it's easier. So here, lambda equals, and also if in solving for z, you would have to ensure that lambda is not 0, which it wouldn't be, but that would be something you have to take into account because you would have to divide by lambda to solve for z. Here, I'm just multiplying both sides by this z, which is in the denominator, which I know is not 0. So this gives me that lambda equals 2 over z squared. I'm sorry, multiplying both sides by, I am dividing both sides by z in this scenario, in the case that I'm doing it, and I already know that z is not 0. So this gives me lambda equals 2 over z squared. All right. So now I've used 1, I've used 4, I've used 2. The only thing I have left now is to use 3. So I'm going to take this and put it into 3. When I put that into 3, we get 2z equals 2 over z squared times negative y. So I'm going to change that negative y so I have z's everywhere. So 2z equals lambda, which is 2 over z squared, times negative y, but we're dealing with all of this information right here. So negative y is the same as 1 over z. So times 1 over z, which makes our lives easier because now we just have z's in here. We can just solve this for z. So now when we solve this for z, the 2's are going to cancel, and then we multiply both sides by z cubed, and we'll get z to the 4th equals 1, which tells us that z is going to be equal to plus or minus 1. And now with that, we have x equals 0, z equals plus or minus 1. You can take that information and you can plug it back into 4, or you can just use this right here because y is the only thing that we're looking for. So we can use whatever is in this group of stuff where we've isolated y and use it there. So when z equals 1, y equals negative 1. So to make sure we don't pair the wrong things together, so z equals 1, and y equals negative 1. And then when z equals negative 1, y equals positive 1. You don't want to accidentally pair this z equals 1 with y equals 1 because that doesn't actually work. So you want to make sure that you pair your things, and you would have extra points in there that are not legitimate points to be considering. So here we got the points x equals 0, y equals negative 1, z equals 1. So we got 0 was negative 1, 1. And then the other point we have is 0 and then 1, negative 1. So those are 2 points that we got just from x equals 0. Now we need to consider this scenario, lambda equals 1. So what I'll do is I will just set that up, and then I will let you all attempt that and hold off, finishing off until our next lecture. So this is lambda equals 1. We'll double underline that. Notice in this process, and if you look at the last problem as well, for this x equals 0, I use 1, 2, 3, and 4. Where's my 4? So I use 1, and then I use 4, and then I use 2, and then I use 3, which means I know I have gotten everything I possibly can out of that because I used all my equations. You don't want to go through and look and see that you have not used an equation unless that equation wasn't giving you any information. So when you go through lambda equals 1, go through that process, make sure you use everything. Don't forget 1 was already used right there. So if you go through this process and you don't see 1, you shouldn't see 1 because you already used 1 to get there. So you should see 2, 3, and 4 and getting your points there. And I'll go and I'll finish this problem at the beginning of our next lecture.